In this lecture, we are going to spend some time discussing the concept of statistical power, which was first introduced in the Principles of Experimental Design. And so statistical power is defined as the probability that a particular experiment will detect a difference, assuming that there really is a difference to be detected. And so this statistical power concept is really essential in the planning process of conducting a research study. And so the four components that have the ability to influence the conclusion of a research project are shown here on this slide. The one that we are going to concentrate the most on is directly related to and interpreted as statistical power, and that is sample size. So the second concept is the effect size. So this really refers to the magnitude of the effect of one factor on the variable that we are trying to measure. So this could be the effect of our treatment factor on the effect of our response variable. So how much of an effect size are we interested in? The third component of that could influence a research project is the level of significance that we use. So we have already talked about the level of significance in research for this class, and for really most sciences is going to be that alpha value of 0.05 or a 95% level of significance. And then all of these things contribute to power, which again is the probability that a particular experiment will detect a difference, assuming that there really is a difference to be detected. All right, so with sample size, we're going to spend quite a bit of time talking about this. And with sample size, this really refers to the number of experimental units that are accessible to the study. And so how many subjects or experimental units we are going to manipulate using our treatments. Okay, so what are we going to apply our treatments to? So some examples of these manipulated subjects are really simply like how many animals do we need in a study? How many plants do we need in a study? How many people do we need in a study in order to adequately study the phenomenon that we're interested in? And so when we determine sample size, this is a critical and important part of this research methodology planning process. And sample size specifically is probably the most important component of this whole entire thing, but unfortunately it's also the most neglected. So some concerns that we have to take into account when we determine sample size are that in a scenario, what happens quite often is that we see allocation of a specific number of plants or animals as experimental units rather than the appropriate number that we need to efficiently detect a difference, if there is one there to detect. And so some things that we have to take into mind when we're trying to figure out how many samples to use or how many experimental units to use is how much is it going to cost for upkeep of these replicates. And so, for example, an animal is really quite a big investment. So just one animal. So for example, if we were going to do a feedlot study where we were going to test two different diets, a control and a treatment diet, and we needed 10 head of animals per treatment, those steers, the growing steers right now, are worth, gosh, if they're 600 pounds, they're probably worth, $750 a piece, plus the time it takes to feed them, plus the cost tied up in the treatment or the diet, plus the cost tied up in labor. All of those things can really compound as you start getting more and more experimental units. So it's important that you make sure that you have the least amount of experimental units as possible to help keep your costs down, but enough experimental units to actually be able to detect a difference if there is one there to detect. And so when we think about what our experimental unit is, this having clarity around this issue is really important. So, for example, is the experimental unit for a research project going to be an individual animal or plant? Is it going to be a pen of animals? Is it going to be an entire greenhouse of plants? Or is it going to be entire fields? Okay, so how we define our experimental unit is really critical in how we interpret and how much pressure we put on our sample size. All right, so if we are dealing with pens of animals that are our experimental unit, the reason we might be doing that is because the pen is the smallest unit that a treatment could be applied to. So for example, if we don't have the ability to have individual feeding records and we have a pen of 8 animals, the diet then gets fed to that entire pen, and you don't have the ability to determine that cow ID number 1 ate this many pounds and cow ID number 2 ate this many pounds. You have to actually measure it on the per pen basis rather than an individual head basis. And then as we extrapolate this out on the plant science side, we really could get into a situation where we are dealing with specific fields. And so this is kind of a cool satellite image. This is actually of a flower farm in Washington State during the bloom. And you can see that they have different species and subspecies of flowers in a lot of different areas here. So the way that we determine what our experimental unit is becomes really, really important depending on what our treatment and our research questions are. So let's talk really quickly about this concept of pseudo-replication. And this is actually a review because you were exposed to this with the principles of experimental design. So pseudo-replication is going to be something that can happen as we are trying to address the concept or the principle of replication. So as a quick reminder, replication is the concept of us manipulating or measuring a response or our dependent variable on a number of experimental units. And so those experimental units are then going to be replicates. And so if we were interested in collecting weaning weight off of an individual steer, we could get a weaning weight off of ID tag number 1. We could get in weaning weight off of animal number 2, number 3, number 4. So those individual animals are replicates in experimental units. And so we can get into a situation where pseudo-replication is actually a problem when we are talking about designing a research project. And pseudo-replication is the failure to have independent replicates. And so this is where we can see things like an entire pen or an entire field having some sort of effect on the experimental units. And so we have to think through what we would have to do in that scenario. And so when we are calculating sample size, we are going to use a power calculation to do that. And so I wanted to give you guys kind of the big ugly formula just in case you ever need this later on down the road if you go into a research discipline at all. But this power calculation is shown here. And so it is n is equal to 2 times t squared times s squared divided by d squared. And so we've got it listed out what each one of these acronyms and letters represent. So n is going to be the number of replicates. So here we are solving for n. T refers to the student's t-value for a chosen probability, and student's t-value is something that we discussed in the statistics section. S refers to the variability of the experimental unit, and variation in most cases is going to be expressed by the standard deviation term. And then D is going to be the size of the difference that we hope to detect. And so, for simplicity's sake, we have actually made this equation a lot simpler, so you guys only had to memorize this equation that is highlighted on the slide, where n equals 8 times the CV squared divided by the size of the difference that we wish to detect. And so this is the power calculation formula that you need to memorize, because we're going to work through some of these power calculations on quizzes and with the respective projects. Some other ways that you can determine how many experimental units you need is through online sources. So Statistical Solutions is linked in here, as is the DSS tool. Those are both good tools to run a simple power calculation. But the one that you need to know for this class, for quizzes and everything else, is this equation highlighted in red. So let's quickly run through an example and how to solve it so everybody is on the same page. Let's assume that you are planning to do a tomato growth study using individual plants. So here, the individual tomato plant would be the experimental unit. There are 6 different plant foods that are going to be tested. So 6 different treatments. The mean CV or coefficient of variation for growth in tomato plants is assumed to be 12%. So you wish to detect differences that are greater than or equal to 8% with a significant value of P equal to 0.05. Okay, so P here, this is our alpha value. Okay, the CV value is going to be 12%. So this, all the information that you need to solve this is actually shown in this problem here. And so the question that we need to solve for is, what is the total number of tomato plants required for this study? All right, so again, we've got the question at the top, so let's work through what this looks like. So we know that our equation is going to be that equation that was highlighted 2 slides ago, where in this case, n is equal to 8 times 12% squared divided by 8% squared. All right, and so to solve this, we just plug in the CV as 0.12, right? So 12%. And we plug in D as the 8%. And so we then can start to just solve for N, and we end up with a total of 18 tomato plants that are going to be needed per treatment in this study. So another step that you could take further is that if we need 18 tomato plants per treatment, how many total plants do we need for the entire study? And that's where you would take 18 times 6 to get the total number of experimental units for the entire study. And so this is a good example to begin to work through in order to determine how many experimental units you need for your research project.